welcome to a new discussion of this Remote Sensing Essentials course. And today we are going to discuss three things. One is spatial filtering. Earlier few times I have mentioned this thing, and also band ratioing, and I will be showing through software demonstration later on. And a third technique is principal component analysis technique. So, band ratioing and principal component analysis techniques are performed on multispectral data, whereas the spatial filtering technique can be performed on a single band or on a color composite also. But band ratioing, of course, you require minimum 2 number of bands, and for principal component analysis you require at least 4 bands to perform this one. So, we will start first with the spatial filtering technique, and these are also called local operations. Basically the main purpose of this thing, after the enhancement, if we want to see more sharpness in the image or more smoothing in the image, then we go for this spatial filtering techniques. So, basically also it is called convolution technique or convolution filtering technique. Two main categories of filters spatial filters are known in digital image processing of remote sensing data. There might be some other filters, and the concept of these filtering techniques have come through the electrical or electronics engineering to filter the different waves or noises. Here it is a spatial filter rather than a linear or slit filter. So, we are talking about a spatial filter, not the filter which is generally used for wave noise clearance and other thing. Two main types, one is the low pass filters, basically which emphasize the regional spatial trends, make your image more smoothen, and de-emphasizes local variability. So, whenever you require that you want to see the regional things rather than local things, then low pass filter is employed. And when we want local things should be emphasized, then we go for high pass filter. So, these are the two major things are there for in different types of filters in high pass category, and one we can put as edge enhancement. So, which combines basically both filters, but mainly it focuses on the edges of your main feature. Suppose there is a road, you want to emphasize that road on an image, or a linear feature on a satellite image, maybe a geological feature or some other feature, then for that purpose we use edge enhancement. So, locally the features which you want to emphasize are enhanced, and regional things are not enhanced there. So, as I was just mentioning that if I take this a single wave on the top figure A, it is a combination of 3 waves of different amplitudes and frequency are there. So, if we apply filtering on top figure of different frequencies, this is what we will get. So, the bottom one is showing basically the combination of 3 waves in a total in one waveform. So, that is the in other when you are going for a slit kind of or linear filter, but the filter which we are talking is basically the spatial filter. How these filters looks and how this is performed on an image, this we will be discussing now. Basically these are convolution metrics, and the example which I have taken now is the low pass filter. So, what we will what here we see that is a example of low pass convolution matrix filter. A filter is basically a 2-dimensional matrix that might be a 3 by 3 pixels or maybe 5 by 5 pixels or 7 by. It has to be a odd number. The reason is because for the center pixel which it will calculate the value from that image which is subjected for filtering, in this case low pass filtering. So, if I take more simple example of like the second one, which is having in all cells of this filter, spatial filter, we are having one value. And all this all cell values, suppose this is put here, then corresponding cell values will multiply with whatever the cell value in the filter. Here in our case, all cell values are 1. So, 24 multiply by 1, 26 multiply by 1, and likewise, and then their total divided by 9. So, what will happen? It will create an average value using the surrounding pixels to the center pixel, which is in our this example it is value having 30. So, by which it will smoothen the image, and as a result you can see in the bottom. So, this is the input image which you are seeing here, which has been subjected to low pass filtering, and more smoothening has occurred in this image after this filtering which is given there. So, the only problem in spatial filtering is what happens on the edges, because if I want to calculate a new pixel value through filtering for this corner pixel or the pixels which are on the edges, then I cannot put my this roving matrix over 26, because then I reach to the outside of an image. So, output image will have one row, one column like this on all boundary, one pixel thickness boundary without any values. So, it will not calculate, and that will be stored in the image as well. So, that is the only limitation which we are having for either low pass filtering or high pass filtering, that the edges, one pixel thickness edge, if it is a 3 by 3 pixel spatial filter. If this filter is 5 by 5, then two pixel thickness rows at the bottom and the top, and same in the left and right, will not be considered for spatial filtering. And if I go for 7 by 7, then it would be 3. So, likewise only in the edges we are having problem. So, this is a kind of a trade-off. The purpose here was to smoothen the image, so that I can see the picture more regional features rather than I get distracted because of local variations or local features. For that purpose, a convolution matrix of low pass filter can be applied. The example here also given for the center pixel like this, and all these pixels have been considered while calculating the values, and this is how the low pass filter will work. There can be many other filters which are the examples of high pass filters. Here the purpose here to emphasize the local features and de-emphasize the regional features. Therefore, in all of these examples which are shown here, A, B, C, D up to F, all are having some values, some cell values of this filter are in negative, because the main purpose, remember, is that we want to emphasize the local features. One. So, on the edges of these filters, though we have taken the simplest example, that is 3 by 3 filters, nonetheless some values are always in negative 1, and the center values like here 5, 5, 9, these are higher values. So, what would happen when these filter will go on an image cell pixel for calculating a new pixel value, pixel after pixel throughout that image, then what will happen, because of this high value in the center, that will be used in to emphasize the local features, and at the same time it will de-emphasize the regional features. Whereas, in case of low pass filter, no special treatment for the center pixel, and therefore, like not giving 8 value or 6 value, here every value is the same, because the purpose here is to de-emphasize the local features, which is just opposite to high pass filter, and emphasize the regional features. So, that is just whenever you see this kind of filter matrix and this convolution matrix, whenever you see, if you see any negative value 1 and the center value is high, you can immediately guess that it is a high pass filter. If we are going for edge detection, then we must know that for which direction we want to emphasize the features. That is why there are in some case, like if I take this example, only 2 values are having minus, rest are having positive values. So what is basically the purpose here is by devising matrix based on the more complex algorithms, which is example of B and C. So edge enhancement matrices results from adding the edge detection of the original image, for example D, E and F. So if we know these things, then we can emphasize that I want to enhance the only edges, not all features, local features through high pass filter. So these are the two. Now let us see the example here. This is the example of high pass filter in which the convolution matrix of 11 by 11 pixel, not 3 by 3, not 5 by 5, not 7 by 7, 11 by. Larger the this convolution matrix would be, larger the size of the filter would be, it will encompass large pixel values to calculate the pixel value for the center pixel. And therefore, since it is a high pass filter, so what it has done, it has de-emphasized all regional features, because it is a relatively very large size filter, 11 by 11, and therefore it has de-emphasized the regional features and highly emphasized the local features, and that is what you are seeing, these edges of all these features which were more or less dull in the original image have been emphasized like anything. That you can see the all linear features or edges of all features have come up very clearly. So that is the advantage of high pass filter. However, larger the convolution matrix for spatial filtering is, whether it is a low pass or high pass, more the time it would take for processing. So if you are having a very large image, then in the practice what you should do, you should take a subset of that image and try to perform filtering using same concept. You may be using even 5 by 5 or 7 by 7, and once you are sure that now I want this filtering for entire image, then run for, because if this is more or less subjective or it requires some iterations till you find the output is suitable for your project. Till then you will keep trying different options. So the best thing is create a subset of that image, try all kinds of filtering, and once you are satisfied, then take the entire image and run that filter which is most suitable to you. And in that way you would save lot of time. Otherwise, for large image, for having 11 by 11 convolution matrix will take lot of time for processing. Similarly, directional filtering is also possible. Like edge enhancement, wherever are edges in through high pass filtering, it will be emphasized. But I want in a particular, if I know that there are features, say they are running in east-west direction or in a north-south direction. So I want to emphasize those features, linear features, and for that I will be using directional filtering. Two examples are here. One A is the example for the northward direction. That means the features are in the north-south direction. Now if you see carefully this convolution matrix of 3 by 3, you see that here I am adding more values to my center pixel in northward direction, and whereas in the southward direction I am having negative values, and the same in the southwest direction, same in the southeast direction, though value is -1 in both these corners, but the southern side I am having 2. So that is why it will produce an image which will have more emphasis in the northward direction. And whereas if I want a southward direction, this is the southwest direction in case of B, then I will put the values negative here in opposite corners, and then these values, that means the features which are having orientation north-south direction, they will be emphasized northeast southwest. So here the southwest direction features will be emphasized. So by even looking a filter, a convolution matrix, you you can understand that what effect it is going to be on image once this is used for filtering. So, likewise, not only low pass filter, not only high pass filter, you can use the edge enhancement. For that you sometimes go for a large convolution matrix like in previous example 11 by 11, or also you can use the directional filtering. Let us see now one example here, that this is the input image on the left side, and on the right side you are having the filtered image, directional filtering. So, directional filtering has been done, and what you are seeing that the features which are in the northeast southwest directions like these one, they have been emphasized very significantly, and whereas it is not very easy for anyone to pick up those features very easily in the unprocessed or raw image. So, these what from different directions tends to enhance or disclose linear features, because our aim is to find some linear features present in the image. In many earth sciences related work, in petroleum exploration, groundwater exploration, mineral exploration, these linear features plays very important role, or maybe in many civil engineering projects also. So, therefore, these are required. So, you have to emphasize in one direction, and in convolution matrix that has to be in the opposite direction. So, preferentially near the perpendicular to the transverse direction, and what you are seeing that this filtering has been moved throughout the image except one pixel thickness on all sides. Now, so far what we have been seeing the examples and discussing on single band. However, you can also do the spatial filtering on multispectral images or colored images or color composite, not a problem at all. But these now the so we consider spatial filtering under univariate image statistics or image analysis. Now, we will be discussing multivariate image analysis or image statistics. So, two things, wind ratioing and principal component. So, as you know that in remote sensing we are concerned with the measurement of how much radiant flux is reflected or emitted from an object on more than one band. And because we are involving now more than one band. So, it is useful to compute multivariate statistics which is a measures as a covariance or correlation among several bands, because you know that if you see the band after band in a continuous fashion, you may find that they are sometimes they are highly correlated, and we want to use those bands in our maybe color composites or in some analysis, multispectral analysis, where individual bands are less correlated, and for that purpose we may perform multivariate image statistics. So, band ratio is one of the technique. Principal component, or in short we also call as PCA, maybe feature selections, classification and accuracy assessment. All these will come under this multivariate statistics. First we will go for band ratioing. Band ratioing involves two bands basically, and as if you see in the figure, and some values are also given there, that the solar radiation is coming here, and whatever is from different surfaces. One surface is example is shown limestone, another one is red bed, and then you may be having soil. On one side it is brighted because sun is on this right side, whereas on the left side it is in the shadow. So, the values which you are seeing are different values which are coming after the reflection from different surfaces which you are seeing here. So, it is possible that these values will of course will give different reflection, but if there are three band scenarios are there, red, green and blue. Like if I take this example, that from this surface, this is which is marked yellow here, all are giving almost same reflection. But when we go to the red band, that in the red band or red channel is having value 46, whereas other green and blue are in that band their reflection is just 23. If I go in the shadow side, then the values here instead of 46 all values are 23, but red band is again having maximum, that is 23, and rest are having 11 and 12 because it is in the shadow side. Now, if there is a scattering effect and other things, these values will further be reduced and we might be getting values only up to this much 5, 14, 32. So, if we perform band ratioing, we can exploit these differences which is occurring in different bands and can create new outputs and very useful images to receive. Let us see the example. Here on the left side, band 1, which is the blue radiation, has been which shows that there hardly I can differentiate between different rock units which are present here or land covers which are there. But when I create a band ratio between band 3 and band 2, this is example from Landsat TM, and then I clearly get a clear unit which comes out in the band ratio image, which is not possible in band 1 because of the topography is not allowing us to see that much difference in two litho units. Whereas on the right image, when I create a band, a ratio of band 3 and 2, that removes the effect of topography, illumination effects or differential illumination and will yield the differences in rock types, and this is what the example is. Though output is going to be in black and white, two gray images of band 3 and band 2 in this example have been taken and output is in grayscale. Band 1 does not allow us to differentiate between two major litho units. So, this is one of the best example of this. Now, if I am having too many bands with us, not just 4, but maybe 7, maybe 10 or 20, or in a case of hyperspectral also, then I can create many band ratios of different combinations and then can create a color composite of band ratios. Like here, this is example that these two other ratios, this is 5 band because this is Landsat 7. So, we are having Landsat TM sensor or ETM plus sensor. So, we are having 7 bands. So, the 5/2 ratio is this one, first one on the extreme left. Then this center one is the band 7/4 ratio. And then I can create one more ratio has been created, which is 3/2 as shown earlier, 3/2. So, all these 3 ratios have been taken and a band ratio composite has been created giving this 2 RGB. So, 3/2 band ratio image has been assigned red color, 5/2 has been assigned green color and 7/4 has been assigned blue color. And if we do it, then see that not only now 2 rock units, but different rock units are coming out very clearly. Otherwise, you see if you compare with this first image band 1, one can interpret that everything is almost same as per the rocks are there or land cover is there. But when we see here, now we are seeing there are many at least 5-6 rock units are clearly visible in band ratio image. So, that is the advantage. And so, we have to understand one while creating these combination of band ratios, that how different rocks, different vegetation or different land units would be responding through these spectral curves in different bands. So, band 7 for example is good for showing hydroxyls common in hydrothermally altered rock. This is more specific to our sciences of geology, but in other cases also once we understand the spectral response curves for different bands of different features, then I can create those band combinations, band ratios and then create finally a composite image, which is a bend ratio composite image. So, a normal false color composite image will never give you such results. A single two bends ratio will always create a black and white image. Here using 3 bend ratios and giving RGB scheme, additive color scheme, one can create a beautiful outputs to discriminate different objects, different features, different rocks, different minerals very clearly, very convincingly. So, that is the advantage of. Recall when we have been discussing this color space and false color composite and other things, now those concepts which we have discussed are being used directly here. So, that is why those things were also important. Now, one more bend ratio technique, but little not simple like 5/2 or 4/7. It is now little more calculation is there, and that is a very standard index. There are many indices related to vegetation or snow cover and other surface identification, surface feature identification, but the one which I am going to discuss is normalized difference vegetation index. What is happening in this index? What we are doing? We are taking infrared channel minus red channel. So, blue, green, red, then infrared. In this sequence we get the band. So, first I am putting infrared channel, knowing that in infrared channel the vegetation will have, a healthy vegetation will have the highest reflectance. So, using that channel minus the red channel, these will be the positive quantities definitely, divided by infrared plus red. So, again this would be a larger number than the top one. So, what would happen that you would create an index, and this can be used. Of course, there will be a multiplication factor, and so that we rescale the values between 0 to 255 if 8-bit scenario. So, we multiply by 255 also, and finally we get the output, which is a NDVI index or NDVI image, which will be showing the health of the vegetation, because we have used infrared channel 2 times differently. So, where increases in the red shows, because there is a blue, thus if vegetation is not healthy, then the reflection, this response, spectral response curves of vegetation will shift towards the red rather than remaining maximum in the infrared. So, if red is increases, that will show that vegetation is having stress, not very good chlorophyll content, and so VNI are very near to infrared will be showing higher values. So, by using this index, we can assess even the quality or health of vegetation. For example, here 2 examples are here. One is on the left side you are having a healthy vegetation, in the right side you are having a vegetation under stress, or maybe in case of deciduous trees, these are trees or leaves are about to fall. If this is the scenario, and if we create a vegetation index, what would happen? So, in infrared channel 50%, this is schematic. So, 50% reflection is going back to the sensor in infrared channel in case of healthy vegetation, and whereas in visible, that is the red part of visible channel, it is only 8% which is going. If you compare this with the vegetation under stress or drying up vegetation, only 40% in infrared is going, whereas in the visible red it is going 30%. So, these values have been calculated in the bottom as NDVI. So, 0.5 minus 0.08 and the percentage have been taken here. So, you get 0.72 here. If we rescale in 255, we multiply that value and we can get a pixel value as well. But for time being, let us take 0.72 in case of healthy vegetation of this ratio. Basically, this is also a ratio, and in case of a vegetation going under stress is having just 0.14. So, you can understand very easily that a vegetation which is healthy, having high chlorophyll content, will have a high NDVI value, and whereas a vegetation which is under stress or drying up will have a very less, relatively very less, as in this example, chlorophyll content, and of course less NDVI value. So, that is the advantage. So, simple band, instead of simple band ratio, if we apply the NDVI and normalized difference, because normalized, we normalize by multiplying some factor, or in 8-bit scenario maybe 255, and so when we normalize it, we get a index, and that tells us the health of a vegetation. If we see in form of images, this is the scenario. This is the first image on the left side is June 2003 of some parts of Europe, and it is completely covering United Kingdom and Ireland, Northern Ireland too. And see the in that part of the world, in month of June the NDVI values are very high, whereas in the month of October, when winter is approaching in that part of the world, the NDVI values are going very less, as you can see. Because green color, the NDVI 1 means the highest NDVI here. So, hardly there are only few places where you are getting green, otherwise rest are going in very less value. So, these values keep changing season to season, and they tells us, and if not season, but if in a forest cover area, if some areas are showing less NDVI value, there might be because of vegetation are under stress, maybe because of some maybe some ailment, some attack by some bacteria or whatever, and that may destroy the vegetation, or maybe lack of water. Sometimes in a hilly terrain, if a slope is moving very slowly, then vegetation also gets dry, and that can also be picked up through this analysis, NDVI analysis, and we can demarcate the area also but after the field verification. Now, the last part here is the principal component analysis, which is very interesting and very useful also. The scenario which the figures which you are seeing basically is showing the example from 2 bands only, and the left one is nothing but a scatter plot. So, what is band 1 versus band 2, and you see they are highly correlated band. Nonetheless, here the origin of this scatter plot is here in the bottom left corner. Now, in order to calculate principal component analysis, first I am going to explain through graphics, and then the origin is basically shifted, instead of in the bottom left corner, it is shifted to the center of this cluster of correlated pixels between 2 different bands, like here it is shown, and the one where maximum correlation is there, that is assigned principal component 1. Maximum variations which are there are assigned principal component 1, and the one which is having relatively less variations compared to principal 1, perpendicular to PC1 is assigned PC2. Now, if I am having a 3D in 3-dimensional scatter plot, then I can have one more principal component, and but that is based on the graphics. But think from if I am having 7 bands and I want to calculate principal component analysis through programming or through mathematics, it is possible, but in graphics only 3 dimensions can be shown. Nonetheless, so what, because of band correlations, as I have mentioned, one see that band 1 is not so much different from what band 2 sees, and this is what the example is. So, as per linear algebra, we are making eigenvectors where eigenvalues contains the contribution of each band to the principal component. So, this is how the calculation is done. Now, there are 7 bands scenario is taken in case of Landsat TM, and what you are seeing 6 components. Now see this one is having the maximum variations present among pixel values will go in principal component 1 because of a high correlation among bands also. So through principal component analysis, the PC1 will always carry the maximum variations. So PC1 here, the top left is showing the maximum variation, and the principal component 6 generally will carry the noises. So one can also use this technique to remove noises from these bands like this. Now you are having a principal component 1 which is having the maximum variations present among pixels are stored in PC1. Then next is the PC2 which is here on the top right, and then PC3. Like in NDVI, we created a color composite using 3 band ratios combinations. Similarly here also it is possible to create color composite using principal 1, PC1, PC2 and PC3. And in 4 as you can see are also variations, but the noise or stripping effects is visible here. 5th and 6th is having maximum noise. This is how the you will get the correlation matrix, and of course eigen correlation vectors also you will get for. So band 1, band 2, band 3, 4, 5, 6 bands have been used here, and against the band PC1, PC2, PC3 and likewise. And all these statistical analysis will be performed, and you can achieve if you create a color composite of principal 1, PC1, PC2, PC3 giving a RGB scheme, you will end up with a beautiful image, beautiful in sense that it will give you a better interpretation, more discrimination among objects. Because 6 bands combination, color combination cannot be possible. By principal component analysis, not only you are removing the errors from the data, but you are gathering all variations which are present in 7 or 6 bands into just 3 components and then creating a color composite. Now little variation in principal component, and that more correlation, more variations can be created by employing a technique which is called decorrelation stretch, which can be done only after the principal component analysis. Here is the example, the same example band 1 and band 2, highly correlated bands are there, and in case of band 3, band 5 less correlation is there. When we go for band 7 and band 4 lens at TM, we see that less correlation exists. So what in decorrelation, what is done basically, I will explain here, that the stretches are made in both the components. Here no stretches are made in these output images, linear stretches, and we can linearly stretch these components and can do the decorrelation stretch. That is why we are decorrelating. These are the correlated bands, and if I create principal component 1, that would be in this direction, of course an origin would be here in the center of this cluster. So I will linearly stretch them, and if I linearly stretch them, that means I am decorrelating them, and by this I am doing more, generating more variations among bands. In 3-dimensional, there are in all these planes and in the center all these bands are shown, and they are respectively are very highly correlated. After DCH, decorrelation stretch, in RGB color space, this is what you see, and after DC, this is in yellow and violet and other color space in a different combinations, you see this one, and then you can have after DCH HSY that or also IHS, that is intensity, hue and saturation, here intensity, saturation in yellow color. But the main important point is here that the original plot may look like this, but when you do the decorrelation stretch, it would look like this. That means you have decorrelated each correlation among bands and will have a maximum variation. Example, this is simple RGB image having of course 3 bands here. Now this is example from Landsat TM. Now there are 6 bands have been taken for the analysis, 3 components have been created. These 3 components have been decorrelated again, principal component 1, 2, 3, and after that a color composite has been created, and this is what is decorrelated image. Now see that what kind of the variations it has created among pixel values for better interpretation and distinguishing different objects very easily. As you can see in the you can see the large differences between a simple RGB false color composite and the decorrelated image. Of course, color scheme will definitely change, one has to care about that while doing the interpretations, but it is bringing many features very clearly which is otherwise was not possible in simple RGB image or false color composite image. So this brings to the end of this discussion. We started with just to recap everything or summarize. We started with the this band ratio things. Before that spatial filtering, 2-3 types of filtering: high pass, low pass filter, edge enhancement and directional filtering. And then edge enhancement and high pass are same, but in edge enhancement you take generally a large convolution matrix. Then we discussed the band ratios composites also, and then we discussed the NDVI, how to assess the health of the vegetation using remote sensing data. This is a very standard thing at global scale, it is being done regularly, and since now we are having more than 48 years of data available, so therefore people are also using NDVI as indication of indirect effects of global warming and climate change. So those kind of studies are also being done using NDVI images, and then we also discuss principal component analysis, and finally we discuss about decorrelation stretch. So this brings to the end of this discussion. Thank you very much.